So the next thing we're going to be looking at is how to continue solving these trig equations but using factoring. And now, instead of trying to solve these trig equations in full generality, we're only going to be asked to find the solutions on this interval. So we'll talk about what that means in a second. So let's say we're going to use factoring. So I can look at this first problem, and right off the bat I notice that both of these two terms that I see, so this term and this term, they have a GCF of cosine. So I can take out a cosine from both of these two terms. I can factor that out. Let's see what I have left. So if I take one cosine out of this, I'll still have the 2 left, and there will be one cosine left as well. And if I take out the cosine from this and factor that out, all I'll have left is root 3. Now at this point I'm going to use the zero product property that says I can take these two factors, so cosine x is a factor and all of this part there is a factor as well, and I can separate them and set them both equal to 0. Cosine x is equal to 0, and that whole other mess there is also equal to 0. So this would be applying the same property that we would see in maybe a simpler problem like x squared minus 2x, where we factor out an x from both terms, and then according to the zero product property we're allowed to take both of those and set those equal to 0, and then we could solve to find our solution. So here our solution would be x equals 0, where the other one would be x equals 2. So same principle is being applied when we're doing this here. So now for our first equation, we're doing the same thing as we did above in the last video. So we're trying to figure out what input is going to allow me to have an output of 0 for my cosine function. So I'm going to go straight to graphing for this. And where is my output going to be? 0. So it looks like there's some solutions. And remember, I'm only considering the solutions on the interval from 0 to 2 pi. 0 I want to include, and I want to get really, really close to 2 pi, but I'm not going to include the value of 2 pi. So I'm going to erect some walls really quick. So let's put this wall here and another wall at 2 pi, and I'm only looking for solutions that end up landing in between the red line and the blue line, including the red line, not including the blue line. So it looks like I get an output of 0 at pi over 2 and 3 pi over 2. So those would be two solutions. And I don't need to put that plus 2 pi in because I'm not considering this infinitely. I'm only looking at those two solutions. Alright, next one. So I can come over to this, and if I add over the root 3 and then divide by 2, I want to know where is my cosine function. What input is going to give me root 3 over 2. So in between the red and the blue line, in between 0 and 2 pi, I see that it's giving me a solution at pi over 6 and 11 pi over 6. So altogether, these four would be all of the solutions in this interval for this trig equation. Okay, so now in the next problem, what I'm noticing right off the bat is that between these two terms, they both have cotangent in common. So I'm going to go ahead and take this entire term here, and I'm going to move it over to the other side of the equation. So I'll simply do that by subtracting it over to the other side. So let's say we do that. So we should end up getting cotangent cosine squared x. We just subtract it over to cotangent x, and then the other side, since we subtracted that, is equal to 0. Alright, so from these two terms I can factor out the GCF of cotangent. So I get cosine squared x minus 2. Alright, then I will use the zero product property, set cotangent x equal to 0, and cosine squared x minus 2 is equal to 0 as well. So let's start solving for the first one. So we'll change this to cotangent. I want to know where's my output going to be 0, and I still have my walls here that I'm looking at. So it looks like at these two values, pi over 2 and 3 pi over 2, I have solutions. Now let's start solving the other one a little bit further. So I can add 2 over to the other side, and then in one step I will go ahead and take the square root of both sides. So I should get plus or minus square root of 2. Now, there's actually a little problem with solving this equation. I want you to see if you can figure it out before I tell you right now. So let's go ahead and change this to cosine. And I want to know, where's my output going to be positive or negative square root of 2? So let's try the positive one first. So positive square root of 2. And this is what I'm getting. So looking at this, there's no place where we're getting an output of square root of 2. The black line is not crossing our cosine function at all, so there's no solution between the two of them. Or even if I do the negative version, it's still a little bit too low or too high. This is because cosine can't have an output that is greater than 1. Just normal cosine can't have an output that's greater than 1. For this, there's actually going to be no solution. There was no place that this intersected that we got a solution. There's no input I could plug in that would give me an output of positive or negative square root of 2. So even though this part has no solution, we did get 2 solutions from the first part when we solved this. So our final answer is just pi over 2 and 3 pi over 2, and we're just going to ignore this no solution part here. This didn't produce any solutions that we can use as our answer. Okay, so the next part here, we're going to go beyond just using the GCF to factor. So now, in this particular problem, I'm noticing that I have 4 different terms. Okay, so the first thing that's popping into my mind is, hey, maybe I can use grouping, which is a strategy in factoring where you group the first 2 terms together and the last 2 terms, and then out of those 2 separately we see if there's a GCF. So let's take a look at the first 2, and I notice that I can factor out 2 tangents from both of these. So let's take out tangent squared, 2 tangents. And if I do that, in the first term I have 1 tangent that's left over, and I've taken everything out of this term, so all that's left is 1 as a placeholder. Alright, then the next 2 terms, again, I want to factor this in such a way that it ends up looking just like what I have in parentheses here. So if I factor out a -1, or in other words, if I divide both of these terms by -1, I'm going to get this result. So if I take negative tangent and I divide that by -1, I get positive tangent. And if I take 1, divide that by -1, I get -1. And so now, because both of these end up being the same, we can continue using grouping, and we'll take 3 tangent squared x minus 1. That goes together in one set of parentheses, and those come together in the other set. Okay, continue using the zero product property, and I'll start with this one on the left-hand side. So first I'm going to add 1 over and then divide by 3 and take the square root. So plus or minus square root of 1/3. For the other one, I end up getting 1. So let's go ahead and change this to tangent, and I want to know, where is this going to give me a value of, let's do positive square root of 1/3 first. So let's see it, pi over 6 and 7 pi over 6. And then now I'll consider the negative version, and that's going to be at 5 pi over 6 and 11 pi over 6. Alright, and then the last one here, I just want to know where I'm going to get an output of 1. So pi over 4 and 5 pi over 4. So all of these values will end up being the solutions that we see in this interval for this Trig equation. And then finally the last one, another strategy I might suggest when you're working with a problem like, for example, number 3, is if it's a lot to look at all the tangents going on, you could potentially rewrite this so there's no tangents in it at all, and it might be a little bit easier to look at. So let's say we rewrote this. So it was 3x cubed minus 3x squared minus x plus 1 equals 0. So now that all the tangents are gone, you could factor this just like normal, and then at the end, put the tangents back in. So that's the strategy I'm going to try to use for the last problem that I see here. So let's pretend the signs aren't there, and I'll write this as 2x squared minus x minus 1 equals 0. So this is just a complex ABC because our a is bigger than 1, so I'm going to go ahead and take my a and my c to a -1, multiply those together, I get -2, and I'm thinking of two numbers that multiply to make -2, and they add to make -1. So if I make 2 negative and 1 positive, those will multiply to make -2 and add to make -1. So this is the one where I'm replacing this middle term with these two terms that I see here. So I'm replacing it with 1x and -2x, and I'll just keep the first and the last term as they are. All right, and then now it's set up so that we can continue to do grouping again, just like the last problem. So I'll group those two as well as the last two. So from the first two, I see that I can take out a GCF of x. So I have 2x plus 1 that's left over. And then from the last two, I want it to look just like, again, what's inside the parentheses here. So I can factor out a -1. And if I divide, I get positive 2x and positive 1. Continue finishing off grouping, I get this. And now I can go ahead and change this after I use the zero product property to what it was before. So I can put the sign functions back in with the x's where they are. So I can rewrite this as sine x minus 1. You're using the zero product property, that's equal to 0. And 2 sine x plus 1 equals 0. Okay, so add over 1, and now let's go ahead and change this to sine. Where's my output going to be 1? So it looks like just at pi over 2 for the first one. And this one, if I solve it, I end up getting -1/2. So where's my output going to be -1/2? So 7 pi over 6 and 11 pi over 6. So all three of these are my solutions. Now for all the problems that we just did, I use graphing the whole way throughout. You could use the unit circle if you prefer to use that method instead. For some of these, you might have been able to tell right away, hey, for example, like sine of x equals -1/2. Okay, I know I could look at the unit circle and find out where the y-coordinate is -1/2, and it would be at these two places on the unit circle. So feel free to use either one, and again, depending on the teacher that you have for calculus, one might prefer one way over the other. So make sure that you're comfortable using either of those ways.